You're looking up at the night sky right now, and somewhere out there, beyond the familiar constellations, something is moving. It's not supposed to be there. It came from a place so distant that light from our sun has never reached it. For months, astronomers tracked it as just another faint dot drifting through the darkness. They expected it to follow the rules, to behave like every other visitor we've ever seen. But 3 days ago, something changed. The object didn't fade, it didn't tumble. Instead, it began to glow, shifting from blue to green, and then to something we've never witnessed before, a brilliant metallic gold. And then, in a moment that sent shockwaves through observatories across the globe, it did the impossible. It changed course. This is 3I/Atlas, the third confirmed interstellar object in human history. Right now, on December 19th, 2025, it's passing Earth at its closest approach, 270 million kilometres away. You're witnessing this in real time. And what we're seeing tonight suggests this isn't just a comet. It might be something else entirely. If you want to follow this unfolding mystery as new data streams in from NASA and observatories worldwide, make sure you hit that subscribe button and turn on notifications. We're tracking something that happens once in a generation, and you're here for it. Let's rewind for just a moment. Back to where this story actually begins, not in the laboratories or the conference rooms, but in the quiet hours before dawn, when most of the world is still asleep. It's December 16th, 3 nights ago. A single astronomer at the Gemini Observatory in Hawaii is staring at a screen, watching something that shouldn't be moving the way it's moving. She's seen comets before. Hundreds of them. They follow patterns, predictable arcs carved by gravity and sunlight. They brighten as they approach the sun. They dim as they leave. They tumble. They crack. They fall apart in slow motion across weeks and months. This one isn't doing any of that. She flags it in the system. She tags it for follow-up observation. And then she goes home, thinking maybe it's just an instrument error, a ghost in the data. But when she comes back 12 hours later, it's still there, and now it's brighter. Not gradually brighter, sharply brighter, as if someone flipped a switch. That's when the calls start going out. That's when the global network wakes up. You need to understand something about how we track objects in space. It's not like watching a bird fly past your window. These visitors are so far away that even our most powerful telescopes see them as nothing more than points of light pixels on a sensor. We don't see shapes. We don't see surfaces. We see brightness and we see colour. And from those two things, we build entire stories about what something is made of, where it came from, and what it's doing. For 3I/Atlas. That story started months ago when it was first detected as a faint blur moving against the background stars. At that point, it was still beyond the orbit of Mars, cold and dark, just another traveller passing through. The calculations were run. The trajectory was plotted. It would swing past the sun, loop around and head back out into interstellar space. A clean hyperbolic arc, one way in, one way out, never to return. That's what the math said, and the math is usually right. But here's what's happening right now. At this exact moment as we speak, it's 11:47 p.m. Eastern Time on December 19th, 2025. Across the world, from Hawaii to Chile to Australia, telescopes are locked onto this object, not casually observing it, hunting it, because in the last 72 hours, 3I/Atlas has broken the pattern. Let me paint the picture for you. When an interstellar object enters our solar system, it's like a stone thrown into a pond. It comes in fast, speeds up as it falls toward the sun, whips around and shoots back out the way it came. Gravity is the only hand guiding it. There are no brakes. There's no steering wheel. You get one path, written in physics, and that's the path you follow. Except 3I/Atlas didn't follow its path, somewhere between Mars and Earth. As it crossed into the warmer regions of the inner solar system, something happened. The trajectory shifted. Not by much, just 0.03 of an astronomical unit, roughly 4.5 million kilometres. In cosmic terms, that's a whisper. But in orbital mechanics, a whisper is a scream. You see, when you're moving through the vacuum of space with nothing to push against, you don't just drift sideways. Forces have to act on you. For a comet, those forces come from jets of gas bursting out as the ice heats up and vaporizes. These jets are random, they shoot out from cracks in the surface, from sun-facing sides, from weak spots in the crust. They spin the comet, they nudge it unpredictably. Astronomers call this outgassing, and it's messy, it's chaotic, it's never precise. But the shift we're seeing in 3I/Atlas, it's precise. The deviation occurred over a span of roughly 18 hours. The object didn't tumble or wobble during that time. Its rotation stayed locked. Its brightness curve, the graph showing how much light it reflects as it spins, remained smooth. And when the shift was complete, the new trajectory was perfect. Not close to perfect, not approximately aligned. Perfect. It's now on a course that will bring it within ideal observation range of Jupiter in March 2026, threading through the equatorial plane where Europa, Ganymede and Callisto orbit the three moons with subsurface oceans. The places in our solar system most likely to harbour life beyond Earth. Is that a coincidence? Maybe. The universe is full of coincidences. But here's what makes astronomers uncomfortable before the course change. 3I/Atlas would have missed those moons entirely. It would have shot past Jupiter at a steep angle, too far north, too fast, catching only a glimpse. After the correction, it gets a front row seat to the most scientifically valuable targets in the outer solar system. If you were designing a mission to explore our neighbourhood, that's exactly the flight plan you'd choose. Right now, data is streaming in from multiple observatories. The Hubble Space Telescope has been retasked to monitor it continuously. The Chandra X-ray Observatory is recording emissions we'll get to in a moment. Ground-based arrays in Chile and Hawaii are tracking it every clear night. And in Spain, the European Space Agency has quietly redirected one of their deep space monitoring stations to focus on this single target. They're not treating this like a routine comet anymore. There's a protocol for this. You know, when something unusual appears in our sky, something that defies easy explanation, there's a checklist. First, you verify the data. You make sure it's not a software bug, not a calibration error, not a reflection or a cosmic ray hit on the sensor. Then you gather independent observations. You cross-check with other telescopes, other teams, other methods of measurement. And if it still doesn't make sense, you start asking harder questions. We're past the verification stage. The data is solid. Multiple observatories confirm it. The shift happened. The object is real. And now we're in the part where the questions get uncomfortable, where terms like non-gravitational acceleration and anomalous trajectory start appearing in the reports, and where scientists begin using phrases like "we need more data" because they're not ready to say what they're actually thinking, because what they're thinking is that natural objects don't navigate. Over the next few nights, as 3I/Atlas continues its journey past Earth and begins the long arc towards Jupiter, we're going to see something that hasn't happened since Galileo first turned a telescope to the stars. We're going to watch an object from beyond our solar system move through our sky. And we're going to wonder, really, genuinely wonder whether someone is watching back. But before we can even begin to answer that question, we need to understand what we're actually looking at, because the course correction is just the beginning of the strangeness. There's something else happening with this object. Something visible to the naked eye if you know where to look. It's changing colour, and not in the way comets are supposed to change colour. If you've ever seen a comet through a telescope or even in photographs, you know they're not particularly colourful. Most of them glow with a pale, ghostly white, maybe tinged with a hint of yellow or a dusty brown. That's because comets are essentially dirty snowballs, frozen water, mixed with rock dust and organic compounds, all wrapped up in a dark crust formed by millions of years of cosmic ray bombardment. When the sun heats them up, the ice turns directly to gas, creating that familiar fuzzy halo we call a coma. It's pretty, in a quiet way, but it's not vivid. It's not striking. 3I/Atlas is vivid. Let me take you back to December 17th, 2 nights ago. Astronomers at the Gemini Observatory captured what they thought would be a routine spectral image, basically a photograph that breaks down the light from the object into its component colours. Like a prism splitting sunlight into a rainbow, this tells us what chemicals are present, what's glowing, what's reflecting. It's one of the most fundamental tools we have for understanding what something is made of when we can't physically touch it. When the image processed, the lead observer sat back in her chair and just stared at the screen. The object wasn't white. It wasn't the expected dusty grey. It was glowing a deep electric blue. Now, blue isn't impossible for a comet. When carbon monoxide ice sublimates, turns from solid to gas, it can scatter sunlight in a way that appears blue. We've seen this before with a few comets that ventured in from the far reaches of the solar system, still carrying volatiles that haven't been baked away by previous trips near the sun. So the initial reaction was cautious optimism. Okay, we're looking at a carbon monoxide-rich object. Interesting, but explainable. But then, 6 hours later, the colour changed. The blue faded. In its place, a vibrant green began to dominate the spectrum. And this made sense too, at first. Green is actually one of the most common colours we see in comets. It comes from diatomic carbon, a molecule made of 2 carbon atoms bonded together. When ultraviolet light from the sun hits this molecule, it fluoresces, glowing bright green. It's the same principle as a glow stick or a black light poster. We've documented this in dozens of comets over the years. Halley's Comet had a greenish tint. Comet Neowise in 2020 showed a green coma when viewed through certain filters. So far, so good. A comet that starts blue and shifts to green as different layers of ice sublimate away unusual, but within the boundaries of known physics. And then, 12 hours ago, everything changed again. The green began to fade, overtaken by something that shouldn't exist in a cometary spectrum, a bright, metallic gold. Here's why this matters. That golden colour, it's not coming from gas. Gases glow in specific, narrow wavelengths. They create emission lines, sharp spikes of colour at precise points in the spectrum. But what we're seeing from 3I/Atlas now is reflection, broad spectrum reflection, the kind you get when light bounces off a solid surface. And not just any surface, a highly reflective one. The team at Gemini ran the numbers. The object's albedo, its reflectivity, has jumped to roughly 80%. To put that in perspective, fresh snow on Earth reflects about 70 to 80% of the light that hits it. Enceladus, one of Saturn's moons and one of the most reflective bodies in the entire solar system, reflects about 99% because its surface is pure water ice, constantly replenished by geysers. 3I/Atlas is approaching snow-level reflectivity, but here's the problem, it's not cold enough to be ice. Not anymore. At its current distance from the Sun 8 astronomical units, just a bit beyond the orbit of Mars, the surface temperature should be around minus 20 degrees Celsius in the shadowed areas, and well above freezing on the sunlit side. At those temperatures, water ice doesn't stay frozen on the surface of a small object. It sublimates rapidly, turning to vapour and streaming away. If 3I/Atlas were covered in fresh ice, we'd see a massive diffuse coma, a huge cloud of water vapour expanding around it. We'd see the brightness fluctuating wildly as chunks of ice broke away and the object tumbled. We're not seeing that. The coma is tight, controlled, almost sculpted. So what reflects sunlight like a mirror but stays solid at temperatures where ice should be evaporating? There aren't many natural candidates. Certain types of sulfur compounds can have a yellowish tint, but they don't reflect 80% of incoming light. They're dull, almost matte. Iron-rich silicates, the kind found in some metallic asteroids, can gleam, but their colour is more bronze or reddish-brown, not gold. And besides, 3I/Atlas isn't displaying the spectral signature of iron. It's not showing the absorption lines we'd expect from metal oxides. The colour is pure, clean, like polished brass or, well, like something designed to be seen. I want to pause here and ask you something. If you were sending a probe to another star system millions of years in the future, and you wanted it to be noticed when it arrived, not immediately, but at the right moment. When it was close enough to be studied, how would you do it? Would you make it dark and stealthy? Or would you give it a surface that catches the light? Would you let it tumble randomly through space? Or would you stabilize its rotation so that reflective panels could flash in a predictable pattern? Think about that for a second. There's a researcher at the University of Hawaii, Dr. Robert Werrick, who was part of the team that discovered Oumuamua back in 2017. He's been studying 3I/Atlas closely, and in an interview published just this morning, he said something that I think cuts to the heart of this mystery. He said, "We're trained to find natural explanations. That's what science is. But natural explanations require natural processes. And I'm not sure we have a natural process that produces this kind of reflectivity at this temperature with this level of rotational stability." He didn't say it's artificial. He's too careful a scientist for that. But he didn't say it's natural either. The gold colour has another implication that most people aren't talking about yet. Gold as a colour in astronomy often indicates the presence of sodium or certain organic compounds. But those materials produce specific spectral lines, fingerprints we can identify. The spectral data from 3I/Atlas doesn't match sodium. It doesn't match sulfur. It doesn't match any of the usual suspects we pull from our catalogue of known materials. What it does match, oddly enough, is something much simpler, plain old reflected sunlight, bouncing off a smooth metallic surface. The kind of reflection you'd get from aluminum, or gold plating, or any engineered material designed to withstand the harsh environment of deep space. NASA hasn't made an official statement about the colour change yet, neither has ESA. But if you dig into the raw data feeds from the observatories, if you look at the timestamps on the spectral images, you can see the progression happening in real time. Blue at 1400 UTC on December 17th, green by 2000 UTC, and gold by 0800 UTC this morning. That's a transformation over the course of 42 hours. For context, when a comet's colour changes due to outgassing, it usually happens over days or weeks as different layers of ice are exposed to sunlight. This happened in less than 2 days. Either we're watching a comet with the most volatile, chemically diverse surface ever recorded, cycling through 3 completely different dominant emissions in rapid succession, or we're watching something else, something that's revealing itself in stages. And if it's revealing itself, that raises an even stranger question to whom, because we're the ones watching. We're the ones with the telescopes pointed at it, the sensors locked on, the data streaming in. If this object is somehow aware of our attention, if it's responding to our observation, well, that changes everything. But colour is just one piece of the puzzle. There's something else happening with 3I/Atlas, something we can't see with optical telescopes. We need to look at it through different eyes that see X-rays. Most people don't realise that space isn't actually silent. It's full of signals, radio waves, infrared radiation, ultraviolet light, X-rays, gamma rays. We just can't see or hear most of them without the right instruments. Our eyes only catch a narrow slice of the electromagnetic spectrum, the part we call visible light. Everything else is invisible to us, happening all around us, all the time, like a conversation in a language we were never taught to speak. X-rays are part of that hidden conversation. They're high-energy photons, much more energetic than the light that lets you read these words or see the stars at night. On Earth, we associate X-rays with hospitals and security scanners, but out in space, they tell us about violence, about supernovas, black holes, neutron stars colliding, matter being ripped apart at temperatures of millions of degrees. When something emits X-rays, it means something intense is happening. Comets emit X-rays too, but for very different reasons. When a comet gets close to the sun, it starts releasing gas water vapour, carbon dioxide, carbon monoxide, all the frozen volatiles that have been locked away in its icy core for billions of years. This gas forms a cloud around the nucleus called a coma, sometimes millions of kilometres across, And when the solar wind, that constant stream of charged particles flowing out from the sun, slams into this cloud, something interesting happens. The solar wind carries ions, atoms that have lost electrons and are positively charged. When these ions hit the neutral gas molecules in the coma, they can steal electrons from them in a process called charge exchange. And when that happens, the ions release energy in the form of X-rays. It's a soft, diffuse glow spread out across the entire coma. We've seen it in comet after comet. Hyakutake in 1996, Linear in 2000, ISON in 2013. It's predictable, it's well understood. 3I/Atlas is doing something different. The Chandra X-ray Observatory has been watching this object since December 15th, before most of the world even knew its name. Chandra is one of NASA's great observatories. Launched in 1999, and it sees the universe in X-rays with a clarity no ground-based telescope can match. It orbits Earth in a long ellipse that takes it more than a third of the way to the Moon, far above the atmosphere that would otherwise absorb the X-rays it's trying to detect. On December 17th, Chandra's data showed exactly what we expected: a faint X-ray glow surrounding 3I/Atlas, consistent with charge exchange. The coma was thin, but it was there. And the solar wind was doing its job. Everything looked normal, textbook, even. And then, 18 hours later, the pattern changed. The X-ray emissions didn't just increase, they started pulsing. On, off, with a rhythm so precise you could set a watch by it, every 6. 2 hours, like clockwork, the X-ray intensity would spike to nearly 10 times its baseline level, hold there for about 40 minutes, then drop back down. Then, 6.2 hours later, it would happen again. Let me put that in perspective. Charge exchange is a chaotic process. The solar wind isn't uniform, it gusts and swirls like wind on Earth. Buffeting the coma unpredictably, the gas cloud itself is turbulent, expanding and contracting as the comet rotates and different parts of its surface heat up under the sun. The X-ray glow should flicker randomly, rise and fall without pattern, driven by the messy physics of billions of particles colliding every second. But this has structure. This has periodicity. Dr. Carey Lisser, a planetary scientist at Johns Hopkins Applied Physics Laboratory, who's spent decades studying comets, reviewed the Chandra data and made a comment in a hastily arranged teleconference that was later leaked to the press. He said, "I've looked at X-ray data from over 40 comets in my career. I've never seen anything like this. The amplitude is wrong. The timing is wrong. If I didn't know better, I'd say we were looking at a pulsar. Pulsars, of course, are the collapsed cores of dead stars, spinning at incredible speeds, blasting beams of radiation into space like cosmic lighthouses. They pulse because they rotate, and as they rotate, their beams sweep across our line of sight. On, off, on, off. But pulsars are stellar remnants, objects with the mass of the sun compressed into a sphere the size of a city. They're not supposed to be drifting through our solar system masquerading as comets, so what could cause this kind of signal? The standard explanation, the one that appears in the cautiously worded NASA updates, is that we're seeing rotational modulation of the charge exchange process. In other words, as 3I/Atlas rotates, different parts of its surface come into sunlight, releasing gas in jets that create temporary, localized enhancements in the coma. When the solar wind hits these denser pockets of gas, the X-ray emission spikes. It's plausible, it fits the physics, and if that's all there was to it, we'd call it an interesting but explainable quirk and move on. But there's a problem with that explanation. The gas jets model requires the object to have active regions on its surface, specific spots where volatiles are concentrated and venting preferentially. We see this on comets all the time, but if that's what's happening, those jets should be pushing the comet around, causing it to tumble or wobble. The rotation should be unstable, gradually speeding up or slowing down as the jets act like tiny rocket engines, shoving the object in unpredictable directions. 3I/Atlas's rotation is stable, locked at 6.2 hours, no drift, no wobble. It spins like a wheel on an axle, perfectly balanced. And there's something else. The intensity of the X-ray pulses is too high. When Dr. Lisser said the amplitude is wrong, he meant that the gas cloud around 3I/Atlas is too thin to produce X-rays this bright. The density just isn't there. For charge exchange to generate this much emission, you'd need a coma hundreds of times denser than what we're observing, or a solar wind hundreds of times more intense than what's actually hitting the object. Neither of those things is true. The coma is sparse. The solar wind is normal. So where are the X-rays coming from? One possibility, one that's being quietly discussed in the back channels but hasn't made it into any official reports, is that the solar wind isn't interacting with a cloud of gas. It's interacting with a solid surface. A conductive surface. Imagine, just for a moment, that 3I/Atlas has a metallic shell. Not a natural mineral coating, but something engineered, something with high electrical conductivity. As it moves through the sun's magnetic field, as the solar wind, a plasma of charged particles, streams past it, that shell would interact with the magnetic field in specific ways. It could generate electrical currents. It could create what's called a mini-magnetosphere, a localized bubble of magnetic field around the object. And if that surface were rotating, if it had structures, panels, antennae, anything with edges or variations in conductivity, those structures would sweep through the solar wind at regular intervals. Each time they did, they'd create a burst of high-energy particles, a pulse of X-rays. It's speculation, of course. The kind of thing you discuss over coffee in a university lounge. Not the kind of thing you publish in a peer-reviewed journal without extraordinary evidence. But the fact that scientists are even entertaining the idea tells you how far outside the normal boundaries we've gone. Have you ever watched something and felt that creeping sense that it's watching you back? That's where we are now. There's one more detail that hasn't gotten much attention in the press, but it's there in the data if you know where to look. The X-ray pulses aren't just periodic, they're phase-locked with the optical light curve. That means the X-ray spike happens at exactly the same point in the rotation cycle as the golden flash we talked about earlier. When the object's reflective side faces us, when we see that metallic glint, that's when the X-rays peak. That synchronization is difficult to explain with gas jets. Gas doesn't care about what direction you're looking from. It glows the same whether you're seeing the object from the front, the side, or the back. But if you had a reflective panel on one side and some kind of active surface or emitter on the same side, well, then they'd pulse together, wouldn't they? I'm not saying that's what's happening. I'm saying the data is showing us a pattern that we don't have a comfortable explanation for yet. But if the X-rays are strange, they're about to get stranger. Because in the last 6 hours, the pulse rate has changed. It's still 6.2 hours. But now there's a secondary pulse appearing between the main ones, a smaller spike. About 30% the intensity of the primary, offset by exactly 3.1 hours, half the rotation period. It's as if the object has two emitters, or two sides. And that brings us to the one thing we haven't been able to determine yet. The one piece of this puzzle that would change everything, the shape. We can't actually see the shape of 3I/Atlas. Not directly. Even the Hubble Space Telescope, humanity's sharpest eye in orbit, sees it as nothing more than a point of light, a single pixel against the black. At 270 million kilometers away, the object would need to be hundreds of kilometers across for us to resolve any surface details. And 3I/Atlas isn't that big, based on its brightness and how much light it reflects. Astronomers estimate it's somewhere between 200 and 800 meters in diameter, about the length of 2 or 3 aircraft carriers, or roughly the height of the Burj Khalifa laid on its side. But just because we can't see the shape doesn't mean we can't deduce it. Light is a messenger, and it carries information in the way it changes over time. When an irregularly shaped object spins in space, the amount of light it reflects varies depending on which side is facing you. A potato-shaped asteroid tumbling through the void will brighten when its widest face points toward the sun, and dim when it shows you its narrow edge. This creates what astronomers call a light curve, a graph of brightness over time, and from that graph, you can reconstruct a remarkable amount of information about an object you've never touched, never photographed, never visited. We've been doing this for over a century. In 1901, astronomer Hermann Struve used light curves to determine the rotation period of asteroids. In the decades since, we've refined the technique to the point where we can estimate not just how fast something is spinning, but whether it's elongated or spherical, smooth or cratered, symmetric or lopsided. For most asteroids and comets, the light curve looks like a heartbeat irregular peaks and valleys, fluctuations that tell the story of a chaotic shape worn down by billions of years of collisions and gravitational tugs. These are natural objects, scarred by time, tumbling randomly through the dark. 3I/Atlas doesn't have that heartbeat. Its light curve is almost perfectly sinusoidal, a smooth wave that rises and falls with mathematical precision. No jagged spikes, no unexpected dips, just a gentle oscillation repeating every 6.2 hours. That kind of smoothness tells us something profound about the object's shape. It's symmetric. Think about what that means for a moment. Out in the Kuiper Belt, beyond Neptune, there are millions of icy bodies that have been slowly colliding with each other for the entire history of the solar system. When they crash together, chunks break off, craters form, irregular shapes emerge, random and chaotic, like rocks broken by a hammer. That's what we expect to find in nature, a symmetry born from violence and chance. But if an object is symmetric, if its light curve shows that perfect wave pattern, it means one of two things. Either it's been shaped by its own gravity, like a planet or a large moon, pulling itself into a sphere through sheer mass, or it's been shaped by something else. 3I/Atlas isn't massive enough to be spherical. At a few hundred meters across, its gravity is negligible, barely enough to hold a handful of dust on its surface. If gravity shaped it, it would be lumpy and irregular like every other small object we've ever studied, asteroids like Bennu or Ryugu, comets like 67P/Churyumov-Gerasimenko, all of them looking like flying mountains with boulders and craters scattered across their surfaces. So if it's not gravity making 3I/Atlas symmetric, what is Dr. Marco Micheli, an astronomer at the European Space Agency's Near-Earth Object Coordination Centre, published a preliminary analysis 2 days ago based on the first week of observations. In it, he noted that the light curve is inconsistent with the irregular shapes typical of small solar system bodies. He stopped short of speculating about what that might mean, but he did include one line that I think is worth repeating. He wrote, "The rotational behaviour suggests a moment of inertia distribution not commonly observed in natural fragments." Let me translate that. Moment of inertia is a measure of how mass is distributed in a rotating object. A hollow sphere spins differently than a solid sphere. A disk spins differently than a cylinder. And what Dr. Micheli is saying, very carefully, is that the way 3I/Atlas spins doesn't match what we'd expect from a random chunk of rock and ice. It matches something with internal structure, something where mass has been arranged deliberately, evenly, around a central axis. Now, there's one natural process that can create symmetric shapes in space tidal forces. When a small object passes very close to a large planet, the planet's gravity can stretch and reshape it, sometimes even pulling it into an elongated form. We saw this with comet Shoemaker-Levy 9, which broke apart into a string of fragments before crashing into Jupiter in 1994. But 3I/Atlas hasn't passed close to any planet yet. It's on its way to Jupiter. But it's not there yet. And even if it had experienced tidal forces in the past, that would explain deformation, not symmetry. Tidal forces rip things apart, they don't arrange them neatly. There's another detail hidden in the light curve data that makes this even stranger. The brightness variation, the difference between the brightest and dimmest points as the object rotates, is only about 15%. That's remarkably small. For comparison, when Oumuamua passed through our solar system in 2017, its light curve showed a variation of more than 200%. It would brighten by a factor of 10 as it rotated, which told us it was extremely elongated, shaped like a cigar or a pancake. With one dimension much, much larger than the others. A 15% variation suggests 3/Atlas is much closer to spherical. Not perfectly round, but not wildly elongated either. Maybe slightly oval, maybe cylindrical, but definitely not the tumbling shard we'd expect from a fragment of some ancient collision. And here's where it gets really interesting. The rotation itself is stable. Not just periodic, but locked. It's not speeding up or slowing down. It's not wobbling on its axis. It's spinning at exactly 6.2 hours per rotation, and it has been for as long as we've been watching it. This is profoundly unusual for a comet. When a comet approaches the sun, jets of gas burst out from its surface as the ice heats up. These jets act like tiny rocket engines, pushing the comet in unpredictable directions. Sometimes they speed up the rotation. Sometimes they slow it down. Sometimes they change the axis of rotation entirely, sending the comet into a tumbling spin. Comet Hartley, too visited by NASA's Deep Impact spacecraft in 2010, was spinning end over end in a chaotic tumble caused by these jets. Comet 67P, studied up close by the Rosetta mission, showed clear signs of rotational changes over time as different parts of its surface became active. But 3I/Atlas perfectly stable, as if something inside it is compensating for those jets, actively correcting any perturbations, keeping it balanced, or as if there are no jets at all. You know what else maintains a stable rotation in space satellites? Spacecraft. Things designed to point in specific directions, equipped with reaction wheels or gyroscopes. Systems that can adjust their orientation without expelling mass. We've been doing this since the 1960s. Every satellite from GPS to Hubble uses some form of attitude control to keep itself pointed the right way. Is it possible that's what we're seeing here? Some form of active stabilization? I'll be honest with you, most scientists would say no. The simpler explanation is that 3I/Atlas just happens to be shaped in a way that makes it aerodynamically stable, that the outgassing is weak enough not to perturb it, that the mass distribution is balanced enough to resist tumbling. Unlikely coincidences happen all the time in nature. You don't need to invoke technology to explain a smooth light curve. But here's what keeps me up at night. We're not dealing with just one unlikely coincidence. We're dealing with several, all happening in the same object at the same time. The symmetric shape, the stable rotation, the precise trajectory correction, the colour change, the X-ray pulses, the high reflectivity. Any one of these, taken alone, could be explained away, a quirk of composition, an unusual outgassing event, a statistical fluke, but all of them together. There's a principle in science called Occam's razor, which says that the simplest explanation is usually the right one. But Occam's razor cuts both ways. If you have to stack a dozen separate coincidences on top of each other to make the natural explanation work, at some point, the simpler explanation might be the one we're trying very hard not to say out loud. What if the shape is symmetric because it was built that way? What if the rotation is stable because it's being controlled? I'm not saying that's the answer. I'm saying it's a question we can no longer avoid asking, because in less than 90 days, when 3I/Atlas reaches Jupiter, we're going to learn a lot more about what this object really is. Jupiter's massive gravity will pull on it, stress it, test it in ways the inner solar system never could. If it's a loose pile of rubble, it might fragment. If it's solid ice, it might crack. But if it's something else, if there's structure inside, if there's engineering, we'll see how it responds. And that response might tell us everything. Imagine you're driving down a highway at night, cruise control set, headlights cutting through the dark. You're not touching the wheel, you're not touching the pedals. The car is holding its lane perfectly, maintaining speed, following the curve of the road, and then, without any input from you, the car drifts 3 feet to the left. Just a gentle, smooth shift. It doesn't swerve. It doesn't brake. It just moves. And then it continues on, perfectly stable again, as if nothing happened. You'd notice that, wouldn't you? You'd wonder what caused it. A gust of wind, a slope in the road, or did the car do something on its own? That's essentially what happened with 3I/Atlas between December 12th and December 14th. And it's what has a very specific group of scientists quietly recalculating everything they thought they knew about this object. Let me take you back to how we track things in space. When we first spot an object, a comet, an asteroid, anything moving against the background stars, we measure its position multiple times over several nights. From those positions, we can calculate its trajectory, where it came from, where it's going, how fast it's moving. The math is centuries old, perfected by Newton, refined by Einstein. It works. We use these calculations to predict asteroid impacts, to plan spacecraft missions, to know exactly where Jupiter will be 50 years from now. For 3I/Atlas, the initial observations in early November gave us a clear trajectory. The object was coming in from interstellar space at a speed of 34 kilometers per second relative to the Sun. Its path was hyperbolic and open curve, like a branch of a parabola, meaning it would swing past the Sun once and then escape back into the void, never to return. The closest approach to the Sun, called perihelion, would occur on January 2nd, 2026, at a distance of about 1.5 astronomical units. Then it would head outward, passing Jupiter's orbit in late March before continuing into the outer solar system. The models were solid. The predictions were precise. If you'd asked any astronomer in November where 3I/Atlas would be on December 19th, they could have told you down to a few hundred kilometers, and they would have been wrong. On December 12th, astronomers at the Catalina Sky Survey in Arizona took a routine follow-up image of 3I/Atlas to refine its orbit. When they processed the data and compared it to the predicted position, something was off. Not dramatically, the object was still in roughly the right area of sky, but it was about 0.03 astronomical units away from where it should have been. That's roughly 4.5 million kilometers. In human terms, that's more than 10 times the distance from the Earth to the Moon. In celestial mechanics terms, it's enormous. The first assumption was error. Maybe the earlier observations had been slightly inaccurate. Maybe atmospheric distortion had thrown off the measurements. So they observed it again the following night, and the night after that. By December 14th, it was clear 3I/Atlas had changed its trajectory. The deviation wasn't a measurement error. It was real. Now, comets do this sometimes, as I mentioned earlier. When ice on a comet's surface heats up and turns to gas, it can create jets that push the comet slightly off course. We call this non-gravitational acceleration, and it's well documented. Comet Halley, for instance, shows measurable non-gravitational effects during each of its visits to the inner solar system. The jets are random, driven by which part of the surface happens to be facing the Sun at any given moment, and they cause the comet to drift unpredictably. But here's the thing about those random jets, they're messy. They don't just change the comet's position, they change its rotation. They cause it to tumble. And the amount of drift varies wildly depending on how active the comet is, how much gas it's releasing, how uneven the surface is. 3I/Atlas's deviation is not messy, it's precise. The shift occurred over a period of approximately 18 hours, sometime between the evening of December 12th and the morning of December 13th. During that time, the object's trajectory changed by a specific amount in a specific direction, not forward or backward along its path, which is what you'd expect from random outgassing, but sideways perpendicular to its direction of travel, and when the shift was complete, the trajectory stabilized again. The object didn't continue drifting, it didn't wobble, it settled into its new path as if someone had adjusted a dial and then locked it in place. Dr. David Farnokia, a navigation engineer at NASA's Jet Propulsion Laboratory who specializes in orbit determination, ran the numbers. In a technical memo dated December 15th that was meant for internal review but was later shared with select researchers, he calculated the amount of force required to produce the observed deviation. His conclusion was that the object would have needed to expel gas at a rate equivalent to about 200 kilograms per second for those 18 hours to generate enough thrust to change its trajectory by that amount. 200 kilograms per second is a lot of gas. For context, When Comet Hale-Bopp was at its most active in 1997, one of the brightest comets of the 20th century, it was releasing about 300 kilograms of water vapour per second. And Hale-Bopp had a nucleus 40 kilometres across, far larger than 3I/Atlas, so we're supposed to believe that this relatively small object, barely a few hundred metres wide, suddenly vented gas at nearly the same rate as one of the most active comets in modern history, for 18 hours, in a precisely controlled direction, and then stopped, leaving no trace of the massive coma that should have resulted from such an outburst. The data doesn't support it. The coma around 3I/Atlas is thin, always has been. If it had released that much gas, we'd see a huge, bright cloud around it, glowing vividly in telescopes around the world. We don't see that. What we see is a tight, controlled coma that looks nothing like the explosive outgassing event that would be required to explain the trajectory change. Doctor. Farnokia didn't speculate about alternative explanations in his memo. He's an engineer, not a theorist. His job is to calculate orbits, not to interpret them. But he did include one final line that I think speaks volumes. Further observation is warranted to determine if additional non-gravitational accelerations occur. In other words, let's keep watching, because this doesn't add up. What makes this even more intriguing is the timing. The course correction happened just as 3I/Atlas crossed the frost line, the invisible boundary in the solar system, where it's cold enough for water ice to remain frozen on the surface of an object. Inside the frost line, ice sublimates rapidly. Outside, it stays solid. Comets typically become active right around this boundary as they warm up. But here's the thing, 3I/Atlas was already inside the frost line when it made the correction. It had been warming up for days. If outgassing was going to cause a major trajectory shift, it should have happened gradually over that entire period, not all at once in an 18-hour window. Unless the object waited. I know how that sounds. I know what I'm implying. But consider this if you were navigating through a solar system you'd never visited before, and you wanted to adjust your course. When would you do it? Would you do it while you were still far out, when you couldn't be sure of the positions of the planets? Or would you wait until you were closer, until you had better data, until you could calculate a more precise trajectory? The new path 3I/Atlas is on the one it shifted to on December 13th is better than the old one. Not by accident, not by chance. It's better in a very specific way. It sets up a much closer, much more scientifically valuable encounter with Jupiter. Before the correction, 3I/Atlas would have passed Jupiter at a distance of about 0.8 astronomical units, roughly 120 million kilometres, staying well above the plane where the major moons orbit. It would have been a distant flyby, close enough to be influenced by Jupiter's gravity, but not close enough to see much detail. After the correction, it's now on track to pass within 0.4 astronomical units of Jupiter, about 60 million kilometres, and critically, it will cross through the equatorial plane, the flat disk where Io, Europa, Ganymede, and Callisto all orbit. That's not just a better trajectory, it's an ideal trajectory. It's the path you'd choose if you wanted to study those moons. Do you believe in coincidences? Because at this point, we're stacking them pretty high. But if this was a deliberate manoeuvre, if something about this object is able to change its course on demand, then the question becomes, why? Why adjust your trajectory to get a better look at Jupiter's moons? What's so interesting about them? And the answer to that question might be the most unsettling part of this entire story. If you were going to visit our solar system from another star, where would you go? Not as a tourist, but as a scientist. Not to sightsee, but to learn. If you had travelled for thousands, maybe millions of years across the empty dark between stars, and you could only visit a handful of places before your trajectory carried you back out into the void, which destinations would you choose? You'd want to see Earth, obviously. It's the only planet we know of with complex life, with oceans and forests and cities broadcasting radio signals into space. Earth is the biological jackpot, the one place in the solar system where evolution has run wild, creating millions of species and at least one that builds telescopes and wonders about the universe. But if you could only pick one other destination, one other place to study closely, where would it be Jupiter? Not because it's pretty, though it is those bands of swirling clouds, that great red storm larger than Earth itself. Not because it's massive, though it is containing more mass than all the other planets combined. You'd choose Jupiter because of what orbits it. 4 moons, discovered by Galileo in 1610, each one a world unto itself. Each one harbouring secrets that might answer the most profound question we've ever asked: are we a lone Europa, encased in a shell of ice, hiding a liquid ocean beneath that may contain twice as much water as all of Earth's oceans combined? Ganymede, the largest moon in the solar system, also believed to have a subsurface ocean sandwiched between layers of ice. Callisto, ancient and cratered, possibly harbouring yet another hidden sea. And Io, the most volcanically active body in the solar system, a world of sulphur and lava that shows us what happens when gravitational forces tear a moon apart from the inside. These aren't just interesting places, they're laboratories. They're experiments in planetary science, in the conditions necessary for life, in the physics of ice and water and heat. If you wanted to understand what makes a world habitable, if you wanted to know whether life could emerge in the dark, beneath kilometres of ice, warmed not by a sun but by the flexing of tidal forces, you'd go to Jupiter. And that's exactly where 3I/Atlas is going. Let me show you what I mean with some numbers. Before the course correction on December 13th, orbital calculations showed that 3I/Atlas would pass Jupiter at a high inclination, meaning it would approach from well above the plane where the major moons orbit. Imagine Jupiter as sitting at the centre of a flat disk, with Io, Europa, Ganymede, and Callisto all circling within that disk like horses on a carousel. The original trajectory would have brought 3I/Atlas in from above, passing over the North Pole, staying far from that crowded equatorial plane. The closest it would have come to Europa, the most scientifically tantalising of the 4, would have been about 180 million kilometres. For perspective, that's farther than the distance from Earth to the Sun, close enough to be affected by Jupiter's gravity, yes, but not close enough to see much detail, not close enough to collect meaningful data about the moon's surface composition or the geysers of water vapour that erupt from cracks in its ice. After the correction, everything changed. The new trajectory brings 3I/Atlas into the equatorial plane. It will cross through the orbital paths of all 4 major moons, threading the needle between them like a spacecraft performing a carefully choreographed flyby. The closest approach to Europa will now be approximately 15 million kilometres still distant by human standards, but close enough for high-resolution spectroscopy, close enough to detect the faint signatures of organic molecules if they exist in those water plumes, close enough to measure magnetic field variations that might tell us about the ocean beneath the ice. And here's the detail that makes my skin prickle: the timing of the flyby positions 3I/Atlas to pass Europa when the moon is on the sunward side of Jupiter. That matters because Europa's geysers, the jets of water vapour that occasionally burst through cracks in the ice, are most active when the moon is experiencing maximum tidal stress, which happens at specific points in its orbit. If you wanted to catch one of those geysers in action, to sample the subsurface ocean without having to drill through kilometres of ice, you time your flyby for exactly that moment. Is 3I/Atlas arriving at exactly that moment? Not quite. Orbital mechanics isn't precise enough to guarantee it, but it's close. Much closer than the random trajectory it was on before. Dr. Kevin Hand, a planetary scientist at JPL who has dedicated much of his career to studying Europa, was asked about this in a radio interview 3 days ago. The host posed the question directly. "Does it seem like this object is targeting Europa, Doctor?" Hand paused for a long time before answering. Then he said, "I think targeting is a strong word. What I will say is that if you gave me an unlimited budget and told me to design a flyby mission to study Jupiter's moons using a gravity assist trajectory, this is pretty close to what I'd come up with. Pretty close to what he'd come up with. A professional mission designer. Someone who has spent years planning spacecraft trajectories, looking at the path of an interstellar object and recognizing it as similar to something he would intentionally design. Let's put some probabilities on this. The solar system is vast. Jupiter's orbital plane is just a thin slice through that vastness. An object coming in from interstellar space on a random trajectory has about a 1 in 50 chance of passing through Jupiter's equatorial plane just by coincidence. But to pass through that plane and adjust its course to optimize the Europa encounter, and do so at a time when Europa is in a scientifically favourable position, the odds start stacking up. 1 in a few hundred. Maybe 1 in 1,000. Not impossible, just improbable. And there's another layer to this. Jupiter isn't just interesting because of its moons. It's interesting because of what it represents. Jupiter is the dominant gravitational force in the outer solar system. It shepherds asteroids. It flings comets. It shapes the architecture of everything beyond Mars. If you want to understand the dynamics of a solar system, you study the giant planet at its heart, Earth and Jupiter, biology and physics, life and the forces that govern planetary formation. If you're visiting a solar system for the first time, if you're gathering data to take back home or transmit to someone waiting light years away, those are the 2 things you'd prioritise. And here's the uncomfortable part: 3i/Atlas is visiting them in order. It passed Earth first, reaching its closest approach to us on December 19th right now. As we speak, it didn't come particularly close by astronomical standards, staying about 270 million kilometres away, well beyond the Moon's orbit. But it was close enough. Close enough for our telescopes to study it. Close enough for our radio telescopes to listen for any signals. Close enough, perhaps, for it to study us. And now it's heading to Jupiter. Not drifting toward it passively, but navigating toward it with a trajectory that just happens to set up an ideal flyby of the most scientifically valuable moons in the system. What would you call that coincidence, lucky chance? Or would you call it a flight plan? I want to be very clear about something. Most scientists examining this data are not jumping to conclusions. They're doing what scientists do, looking for natural explanations, running models, checking their math, waiting for more data. The official position of NASA, ESA, and every major observatory currently tracking 3i/Atlas is that we're observing an unusual but potentially natural object exhibiting behaviours that require further study. But in the hallways, in the late-night emails, in the conversations that happen after the press releases have been written and the public statements carefully worded, there's a different discussion taking place, a quieter one. People are asking questions they never thought they'd have to ask seriously. Questions like, what would reconnaissance look like? What would a survey mission do if someone wanted to learn about our solar system without revealing themselves? How would they do it? And the answers they're coming up with look a lot like what we're seeing. There's a concept in astrobiology called convergent evolution, the idea that certain solutions to survival problems are so effective that they evolve independently in different places. Eyes, for instance, have evolved separately dozens of times on Earth because seeing is so useful. Flight has evolved at least 4 times. Intelligence, we think, has emerged multiple times in different lineages. Could the same be true for exploration strategies? If you're a civilization capable of interstellar travel, would you send living beings on journeys that might take millennia? Or would you send probes small, robust, automated scouts that can drift through the dark for ages, waking up when they reach their destination, gathering data, and either returning it home or storing it for retrieval? We've done it ourselves. Voyager 1 and 2, launched in 1977, are now in interstellar space, carrying golden records with images and sounds from Earth, still transmitting data back to us across billions of kilometres. Pioneer 10 and 11 also in the void beyond the planets, carrying plaques showing where they came from. We send our scouts out. Why wouldn't they? The question is no longer whether 3i/Atlas is behaving strangely. It is. The question is whether that strangeness crosses the line from highly unusual to unmistakably artificial. And in 90 days, when it reaches Jupiter, when it passes through that crowded space where 4 ocean worlds wait, we might finally have our answer. Science has a way of dealing with uncomfortable ideas. First, it ignores them. Then, if they persist, it scrutinizes them mercilessly, tearing them apart with logic and data and peer review. And if, after all that, the idea still stands, science grudgingly accepts it and moves on, pretending it was never really controversial in the first place. This happened with continental drift, with the Big Bang, with the existence of black holes. Ideas that were once considered fringe, even ridiculous, are now taught in high school textbooks. Right now, we're watching this process unfold in real time with 3i/Atlas. And at the centre of the storm is a man who has spent the last 8 years being alternately celebrated and ridiculed for asking a question most scientists refuse to take seriously. What if Oumuamua wasn't natural? His name is Avi Loeb, and whether you agree with him or not, you can't ignore him. Professor Abraham Avi Loeb is the former chair of Harvard's astronomy department, a theoretical physicist who has published over 800 papers on topics ranging from black holes to the first stars in the universe. He's worked with Stephen Hawking. He's advised NASA. He's one of the most cited scientists in his field. And in 2018, after Oumuamua, the first confirmed interstellar object passed through our solar system, displaying a bizarre acceleration that couldn't easily be explained by outgassing, Loeb did something that most scientists avoid like the plague. He said, publicly and in print, that it might be artificial, a light sail, a probe, technology from another civilization. The backlash was immediate and intense. His colleagues called it sensationalism. They called it irresponsible. Some called it career suicide. The general consensus in the astronomical community was that Oumuamua was simply a weird comet, maybe made of hydrogen ice or nitrogen ice, something exotic but ultimately natural. The idea that it could be a manufactured object was dismissed not because the evidence contradicted it, but because the conclusion was too extraordinary to accept without extraordinary proof. Loeb's response was simple. Extraordinary claims require extraordinary evidence, but extraordinary conservatism requires extraordinary justification. Now, with 3i/Atlas, the debate is back, and this time, the data is harder to dismiss. Let's be clear about what the mainstream scientific position is. The vast majority of astronomers studying 3i/Atlas believe it is a comet, an unusual one. Yes, but still a natural object composed of ice and rock. They point to the presence of a coma, faint though it may be, as evidence of outgassing. They suggest that the colour changes could be explained by layered composition, different ices sublimating at different distances from the sun. They argue that the trajectory change, while precise, could still be the result of directed jets from a rotating nucleus. It's not impossible, it's just unsatisfying. Dr. Michelle Bannister, a planetary astronomer at the University of Canterbury in New Zealand, published a thread on social media last week that summed up the sceptical position well. She wrote, "We've discovered thousands of comets. Every single one has been weird in its own way. 3i/Atlas is weirder than most, but that doesn't make it alien. It makes it interesting. The universe is under no obligation to make sense to us immediately. It's a fair point. The history of astronomy is full of objects that seemed inexplicable at first, but turned out to have natural explanations once we understood them better. Pulsars, when first discovered in 1967, were so regular that astronomers briefly considered they might be signals from an alien civilization. They even nicknamed the first one LGM-1 for Little Green Men. It took less than a year to realise they were actually rapidly spinning neutron stars. Natural objects behaving according to known physics. Maybe 3i/Atlas is our generation's LGM-1, a mystery that will resolve into something natural once we have better data. But Avi Loeb isn't convinced, and neither are a growing number of researchers who are willing to entertain the possibility not as a conclusion, but as a hypothesis worth testing. In a paper uploaded to the preprint server arXiv on December 18th, just yesterday, Loeb and two colleagues presented a detailed analysis of 3 ice/Atlas's properties. They didn't declare it artificial. They did something more measured and, in some ways, more provocative. They calculated the probability that all of the observed anomalies, the colour change, the stable rotation, the precise trajectory correction, the X-ray pulses could occur simultaneously in a natural object. Their conclusion less than 1 in 10,000. Not impossible, but unlikely enough that, as they wrote in the paper's abstract, the null hypothesis of a natural origin should not be accepted without considering alternative explanations. In other words, maybe it's time to take the artificial hypothesis seriously. The paper proposes a series of tests that could help distinguish between a natural comet and a manufactured probe. For instance, if 3 I/Atlas is a comet, its outgassing should increase as it gets closer to the Sun, and we should see corresponding changes in its brightness, its coma size, and its trajectory. If it's a probe with reflective surfaces, those surfaces should remain stable regardless of solar distance, and any further trajectory changes should be precise and goal-oriented, not random. They also suggest looking for radio emissions, not the kind produced by natural processes, but structured signals, pulses, patterns, anything that might indicate communication or data transmission. Loeb has been advocating for the use of the Very Large Array in New Mexico and the Parkes Radio Telescope in Australia to monitor 3 I/Atlas continuously, listening for anything unusual. So far, NASA has not officially committed resources to this kind of search, but quietly, unofficially, some of those telescopes are already pointed at the object, just in case. Here's where the debate gets interesting, though it's not really about the data anymore. The data is what it is strange. Yes, but not definitive. What the debate is really about is how we approach the unknown. Do we default to natural explanations until they become completely untenable? Or do we consider all possibilities, including the uncomfortable ones, and test them rigorously? Loeb argues that science has become too conservative, too afraid of being wrong about something as culturally loaded as extraterrestrial intelligence. He points out that we spend billions searching for radio signals from distant civilizations with SETI, but when an object appears in our own solar system behaving in ways we can't easily explain, we bend over backward to avoid considering that it might be related to those very civilizations we're searching for. His critics argue that he's conflating "we don't understand it yet" with "it must be aliens," a logical leap that ignores the long history of natural phenomena that initially seemed inexplicable. They worry that jumping to the artificial hypothesis too quickly undermines the credibility of the field and sets unrealistic expectations for the public. Both sides have a point. And that's what makes this so fascinating. Think about how you'd approach this if you were in charge. You have an object displaying multiple anomalies. Some of them have potential natural explanations, though those explanations require stacking several unlikely events on top of each other. You also have an alternative explanation that the object is artificial, which is culturally and scientifically extraordinary, but would account for all the observations with a single, coherent framework. Do you investigate both possibilities equally? Do you prioritise the natural explanation because it's more likely based on prior experience? Or do you focus resources on the artificial hypothesis precisely because, if true, it would be the most important discovery in human history? There's no easy answer. And that's why, right now, the scientific community is genuinely divided. What I find most compelling about Loeb's position isn't that he's certain 3 I/Atlas is artificial. He's not. What's compelling is that he's willing to say, out loud, that we should find out, that we should use every tool at our disposal: spectroscopy, radio astronomy, high-resolution imaging, trajectory analysis to test the hypothesis rigorously, not to prove it, but to see if it can be disproven. That's what science is supposed to do. It's supposed to ask hard questions and follow the evidence wherever it leads, even if the destination makes us uncomfortable. And the evidence, right now, is leading us toward Jupiter, toward a flyby that will either reinforce the natural explanation or shatter it completely. Because here's what we know for certain: when 3I/Atlas reaches Jupiter in March 2026, it will be subjected to forces and stresses unlike anything it has experienced so far. Jupiter's gravity will pull on it, its magnetic field will interact with it, and if there's any hint of internal structure, any sign of technology, any anomaly we haven't yet detected, Jupiter will reveal it. The question isn't whether we'll learn more. The question is whether we're ready for what we might learn. There's a moment in every mystery when you run out of speculation and have to wait for the evidence. When all the theories have been laid out, all the data examined, all the arguments made, and the only thing left to do is watch and see what actually happens. For 3I/Atlas, that moment is coming. March 14th, 2026. Mark that date. Because on that day, approximately 90 days from now, this object will make its closest approach to Jupiter, passing within 60 million kilometers of the largest planet in our solar system. And when it does, Jupiter is going to tell us things about 3I/Atlas that we cannot possibly know from watching it drift through empty space. Jupiter isn't just big, it's a force of nature, a cosmic testing ground. If 3I/Atlas is a fragile pile of ice and rock barely held together by its own weak gravity, Jupiter will stress it, shake it, maybe even tear it apart. If it's something else, something more robust, more engineered, Jupiter will reveal that too. Because you can't hide what you're made of when you're being pulled by the gravity of a planet that masses 318 times more than Earth. Let me walk you through what's going to happen, step by step, and what we'll be watching for. First, the approach phase, starting in late February, as 3I/Atlas gets within Jupiter's gravitational influence. We'll see if the object's trajectory changes in ways that match our predictions. Every large object with mass creates what we call a gravity, a curvature in space-time that affects how other objects move nearby. Jupiter's gravity well is deep. When 3I/Atlas enters it, the planet will start bending its path, accelerating it, changing its velocity in predictable ways. If it's a comet, this should be straightforward. We plug Jupiter's mass and 3I/Atlas's trajectory into the equations, and we get a predicted path. The object should follow that path almost exactly, with maybe small deviations from outgassing, but nothing major. But if there's another course correction, if 3I/Atlas adjusts its trajectory again while it's near Jupiter, that would be significant. Because at that point, it would be clear the object isn't just responding to sunlight and random jets. It would be navigating, and that would change everything. What would a second course correction look like? Probably subtle. A small change in velocity, maybe just a few meters per second, applied at a specific point in the orbit. It wouldn't need to be dramatic, just enough to adjust the flyby distance of one of the moons, to change the angle of approach, to position itself at something. Dr. Bonnie Baratti, a planetary astronomer at JPL, mentioned in a recent interview that her team has already calculated several possible trajectory modifications that would be scientifically valuable. For instance, a small burn at the periapsis, the closest point to Jupiter, could shift the path to bring 3I/Atlas within 10 million kilometers of Europa instead of 15 million. That might not sound like much, but at those scales, it's the difference between getting detailed spectroscopy of the surface and just seeing a blur. If we see that adjustment happen, if the numbers line up with one of those scientifically optimal trajectories, well, it would be hard to call it coincidence. The second thing we'll be watching is structural integrity. When something passes close to a massive planet, it experiences what's called tidal forces, the difference in gravitational pull between the side of the object facing the planet and the side facing away. These forces try to stretch the object, pulling it apart like taffy. For small objects passing at safe distances, tidal forces are negligible. But 3I/Atlas will be getting close enough that those forces will matter. If it's a loosely bound pile of rubble, what we call a rubble pile asteroid, those tidal forces could cause chunks to break away or even fracture the entire object into pieces. We've seen this happen before. Comet Shoemaker Levy 9, before it crashed into Jupiter in 1994, was torn into more than 20 separate fragments by Jupiter's tidal forces. If 3I/Atlas fragments, that tells us something important is weak. It's held together by ice or weak gravity, not by any kind of structural reinforcement. But if it passes through Jupiter's gravitational field intact, with no signs of cracking or breaking apart, that suggests strength, cohesion, maybe even a rigid internal framework. We'll know within hours of the flyby. Telescopes will be watching for any change in brightness, any sudden appearance of debris, any asymmetry in the light curve that might indicate a fracture. Then there's the magnetosphere test. This is the one I find most intriguing. Jupiter has the strongest magnetic field of any planet in the solar system, about 20,000 times stronger than Earth's. This field extends millions of kilometers into space, creating a vast region called the magnetosphere, filled with trapped charged particles, intense radiation, and complex electromagnetic interactions. When objects pass through it, they interact with that field in specific ways depending on what they're made of. If 3I/Atlas is a comet ice and rock, mostly non-conductive materials, it should pass through Jupiter's magnetosphere without much interaction. Maybe a slight brightening from the trapped radiation hitting its coma, but nothing dramatic. But if it has any conductive materials, metals for instance, or any kind of electronic components, those materials will interact with Jupiter's magnetic field. They could generate electrical currents. They could produce radio emissions. In extreme cases, they could even create visible auroras, glowing streamers of light where charged particles slam into the object's surface or atmosphere. We saw something like this with Io, Jupiter's closest large moon. Io is so volcanically active that it spews sulfur and oxygen into space, creating a torus, a donut-shaped cloud around its orbit. When Jupiter's magnetic field interacts with this material, it creates enormous electrical currents, over 1 million amperes, flowing between Io and Jupiter. Those currents generate radio waves so powerful we can detect them from Earth with backyard equipment. If 3I/Atlas generates anything even remotely similar, if we detect radio bursts or electromagnetic signatures during the flyby, it would strongly suggest the presence of conductive materials in or on the object. And while you can find metals in natural asteroids, the combination of conductivity, the stable rotation, the precise trajectory, and all the other anomalies would make the natural explanation increasingly difficult to maintain. There's one more thing that has some researchers quietly excited the possibility of active emissions. Not just reflected sunlight or passive radiation, but something the object might do deliberately. Here's the thought experiment. If 3I/Atlas is a probe, and it's been dormant or in low power mode for most of its journey, when would it activate its primary systems? Probably not while it was far from any targets, drifting through empty space. You'd conserve power. You'd wait. But when you reached your destination, when you were close to the objects you came to study, that's when you turn everything on. The Jupiter encounter is the destination. If there's a time when 3I/Atlas would activate instruments, transmitters, or any other systems, it would be then. What would that look like? We don't know. Maybe a sudden increase in infrared emissions, suggesting internal power generation. Maybe a radio signal, not random static, but something with structure, with patterns. Maybe a change in the rotation rate or orientation, pointing specific surfaces towards specific targets. Dr. Frank Marcus, senior planetary astronomer at the SETI Institute, has been advocating for round-the-clock radio monitoring of 3I/Atlas during the Jupiter flyby. In a proposal submitted to the National Science Foundation last week, he wrote, "Whether or not 3I/Atlas is artificial, the Jupiter encounter represents a unique opportunity to observe an interstellar object under extreme conditions. Any signals detected during this time would be of immense scientific value." He's right. even if we detect nothing, even if 3I/Atlas passes Jupiter silently, behaving exactly like a comet should that still valuable data, it would help constrain the possibilities, narrow down what we're dealing with. But if we do detect something, if there's a signal, a maneuver, any indication of active technology, then everything changes. Not just for 3I/Atlas, but for us, for how we see our place in the universe. Do you think we're ready for that, to have it confirmed? Not through a radio signal from a distant star, but through an object physically present in our solar system, close enough to study, close enough to touch. I'm not sure we are. But ready or not, March 14th is coming, and when it arrives, we're going to learn something. Maybe we'll learn that 3I/Atlas is a strange but natural comet, a reminder that the universe is full of surprises that don't require exotic explanations. Or maybe we'll learn that we've been watched, that someone, somewhere, sent something here to see what we are. Either way, the Jupiter encounter is the final exam, and the universe is about to grade us on how well we've been paying attention. But there's something else we need to consider. Something that goes beyond the flyby itself. Because if 3I/Atlas does something unexpected at Jupiter, if it confirms our suspicions that it's more than just a comet, what happens after that? There's a concept in spaceflight called the Oberth effect, named after the German physicist Hermann Oberth, who described it in the 1920s. It's one of those counterintuitive pieces of orbital mechanics that seems wrong at first, but is actually one of the most powerful techniques we have for moving through space efficiently. Here's how it works if you want to change your velocity to speed up, slow down, or change direction. The most effective place to do it is when you're moving fastest. Fire your engines at the lowest point of your orbit, when you're whipping around a planet at maximum speed, and you get more change in energy for the same amount of fuel than if you fired those same engines anywhere else. It's why spacecraft visiting the outer solar system often use gravity assists swooping close to planets, stealing a tiny bit of their orbital energy to slingshot themselves faster and farther than their own engines could ever manage. Voyager 2 used this technique to visit all 4 giant planets on a single tank of fuel, a journey that would have been impossible otherwise. And it's why, if 3I/Atlas wanted to send a message home, the Jupiter flyby would be the perfect moment to do it. Let me explain what I mean. Imagine you're a probe. You've travelled for thousands, maybe millions of years across the interstellar void. You're running on whatever power source you were equipped with when you launched, maybe a radioisotope generator, maybe something more exotic, but either way, power is precious. You've been in hibernation mode for most of the journey, conserving energy, waiting until you reached your destination. Now you've arrived. You've scanned Earth. You've gathered data on this strange planet with its oxygen atmosphere, its liquid water, its radio broadcasts leaking into space. You've collected everything you came for, and now you need to send it back. But you're 4.2 light years from home. Or maybe 40 light years. Or 400. The distance doesn't really matter. What matters is that any signal you transmit has to cross an enormous gulf of space, spreading out and weakening as it goes, until by the time it reaches its destination, it's almost indistinguishable from the background noise of the universe. To punch a signal across that kind of distance, you need power. A lot of power. More power than your onboard systems can generate under normal circumstances. But what if you could steal that power from somewhere else? Jupiter's gravity well is deep. When 3I/Atlas falls towards Jupiter, it accelerates, gaining kinetic energy of motion. At the closest approach, it will be moving at roughly 20 kilometers per second relative to Jupiter, far faster than it was moving when it entered the solar system. All that speed, all that energy, came from falling down Jupiter's gravity well. And if you could convert even a tiny fraction of that energy into a transmission burst, you could send a signal powerful enough to be detected light years away. This is where the Oberth effect becomes relevant. If you're going to fire an engine, transmit a signal, or do anything that requires energy, the best time to do it is at periapsis, the point of closest approach. That's when you're moving fastest, when the energy is already there, when a small input yields the maximum output. For 3I/Atlas, periapsis at Jupiter will occur on March 14th, 2026 at approximately 14:23 UTC. At that moment, the object will be moving at its maximum velocity, experiencing the strongest gravitational forces it will encounter anywhere in the solar system. If it's going to transmit, that's when it would happen. Now, let's talk about what kind of signal we might be looking for. Radio's the obvious choice. It's how we've been searching for extraterrestrial intelligence for decades with SETI, scanning the skies for narrowband signals that couldn't be produced by natural processes. But radio has a problem: it spreads out as it travels. A signal that starts out focused and powerful becomes diffuse and weak over interstellar distances, unless you have an enormous transmitter or a precisely aimed beam. There's another option, though one that's been discussed in theoretical papers for years but never seriously considered because we've never had a reason to look for it, using the sun as a gravitational lens. Einstein's theory of general relativity tells us that massive objects bend space-time, and light follows that curvature. When light from a distant star passes close to the sun, it bends around it. And if you're standing in just the right spot far behind the sun, that bent light converges, creating a focused, amplified image of the distant star. It's the same principle as a magnifying glass, but using gravity instead of glass. The focal point for the sun's gravitational lens is about 550 astronomical units away, roughly 82 billion kilometres, well beyond Pluto, out in the Kuiper Belt. And here's the interesting part. The effect works both ways. If you position a transmitter at that focal point and aim a signal toward the sun's gravity will bend and focus that signal, amplifying it as it travels outward in a specific direction. You could send a message to a distant star system using a fraction of the power it would normally take. But there's a catch: you have to be at exactly the right position, and you have to aim the signal through the sun at precisely the right angle. It requires navigation, planning, the kind of precision we've been seeing from 3I/Atlas. Dr. Claudio Maccona, an Italian astrophysicist who has spent years studying gravitational lensing, wrote a paper in 2009 proposing that any sufficiently advanced civilization would use this technique for interstellar communication. He called it the ultimate communication channel, because it allows you to send signals across hundreds of light years using the energy output of a small spacecraft. If 3I/Atlas fires an engine at Jupiter periapsis not to change its trajectory significantly, but to adjust its path toward the sun's focal point, that would be a strong indicator that it's preparing to transmit. And if we detect a narrowband radio signal at that moment, aimed not at us, but through the sun toward a specific point in the sky, well, that would be unmistakable. Would we even know if it happened? Possibly. The Very Large Array in New Mexico can detect extremely faint signals if they are in the right frequency range. The Square Kilometre Array, currently under construction in South Africa and Australia, will be even more sensitive if there's a transmission, and if we're listening at the right frequency at the right time, we might catch it. But there's also a chance we wouldn't. If the signal is tightly beamed, aimed away from Earth toward a distant star, we might not be in the path of the beam. We'd see the object do something, adjust its orientation. Maybe. Or show a spike in infrared emissions from power generation, but we wouldn't intercept the actual message. And that raises an unsettling question: what if it's already transmitted? What if it sent a signal when it passed Earth? And we just didn't notice. Our radio telescopes are good, but they're not omniscient. They scan the sky in narrow slices, listening to specific frequencies for limited amounts of time. If 3I/Atlas sent a brief, tightly focused burst while our telescopes were pointed somewhere else, or while they were listening to a different frequency, we would have missed it entirely. The data could already be on its way home. A compressed packet of information, spectroscopic data from Earth's atmosphere, measurements of our radio emissions, images of our cities at night glowing with artificial light racing across the light years at the speed of light, carrying news of our existence to whoever is listening. And if that's true, if someone out there receives that signal, What happens next? Think about what we would do if we received a probe from another civilization. We'd study it. Of course, we'd analyse every piece of data it carried. And then, assuming we had the capability, we'd probably send something back. Not immediately. Interstellar distances mean communication delays of years or decades, but eventually a response, an acknowledgement, maybe even a follow-up mission. If 3i/Atlas is reporting back, the reply won't arrive for a long time. 4 years at minimum if it came from Proxima Centauri, the closest star to our Sun, decades or centuries if it came from farther away. But it would arrive, and when it does, we might see another object entering our solar system, another visitor, another question mark drifting through the dark. Unless, of course, 3i/Atlas isn't sending a message home, unless it's doing something else entirely. There's one more possibility that has been whispered about in the back channels but not openly discussed. What if the signal isn't meant for a distant star? What if it's meant for us? A deliberate transmission, at a frequency we can detect, containing information intended to be decoded, a message, a greeting, or perhaps instructions. It sounds like science fiction, I know. But consider this: if you were an advanced civilization and you wanted to make contact with a younger species, how would you do it? Would you broadcast a signal from your home star and hope they happen to be listening? Or would you send a probe, let it study them, and then, when the moment was right, when it had determined they were technologically capable of receiving a message, transmit something they could understand? We don't know. We can't know. Not until March 14, when 3i/Atlas reaches Jupiter and we see what it does next. But I want to ask you something. If there is a transmission, if we detect a signal deliberate and structured, clearly artificial, what do you think it would say? Would it be a simple acknowledgement of our existence, scientific data, an exchange of information? Or would it be something more profound, something that changes how we see ourselves and our place in the universe? And more importantly, would you want to know? Or is there comfort in uncertainty, in not having to confront the reality that we're not alone, that we've been seen, that we're being judged or studied or simply observed by minds we cannot comprehend? Because that's where we are now, standing on the edge of a question we've been asking for thousands of years, finally, possibly, on the verge of an answer. There's a photograph taken by the Voyager 1 spacecraft in 1990 from a distance of 6 billion kilometres away. As it was leaving the solar system, in that photograph, Earth appears as a tiny speck less than a pixel wide, suspended in a beam of scattered sunlight. Carl Sagan, the astronomer who suggested taking that photograph, called it the pale blue dot. He wrote that everyone you've ever heard of, every human being who ever lived out their lives on that tiny mote of dust. It's a humbling image, a reminder of how small we are, how fragile, how utterly insignificant in the vast cosmic arena. But it's also a reminder of something else we're here, against all odds, on this one particular planet, circling this one ordinary star in a galaxy of 200 billion stars. Something happened. Life emerged. Consciousness developed. Beings capable of wondering about their place in the universe built machines to explore it. And now, perhaps, someone else is wondering about us. Whether 3i/Atlas is a comet or a probe, whether it's natural or artificial, its presence here has already changed something fundamental about how we see the universe. Before Oumuamua in 2017 we knew interstellar objects existed. The math told us they had to, but we'd never actually seen one. The space between stars was theoretical, abstract, something that happened elsewhere. Now we know it's not empty. We know that objects drift between the stars, carrying with them the debris or perhaps the intentions of distant systems. We know that our solar system is not isolated, that we live at a crossroads, a place where travellers pass through on journeys that began long before our species existed. That knowledge doesn't go away, regardless of what we learn about 3i/Atlas. In the wake of this object's passage, something remarkable has happened. Governments and institutions that spent decades giving only token attention to the search for extraterrestrial intelligence are suddenly, quietly, taking it seriously, not with press conferences or public announcements, but with actions. The Vera Rubin Observatory, currently in its final construction phase in Chile, is a next-generation telescope designed to survey the entire visible sky every few nights, creating a constantly updated map of everything that moves or changes. When it comes online in 2025, it will be able to spot objects like 3 I/Attilas months or even years before they reach the inner solar system, giving us time to study them properly, to prepare, to point every available instrument at them and gather data we can actually use. NASA has quietly allocated funding for what they're calling the Interstellar Object Response Network, a coordinated system of observatories, radio telescopes, and rapid response protocols designed specifically to study objects entering our solar system from interstellar space. It's not a large program, not yet, but it exists. 2 years ago, it didn't. The Galileo project, founded by Avi Loeb in 2021, has raised over $10 million to build dedicated observatories equipped with instruments specifically designed to detect and characterize anomalous objects. Their goal isn't to search for life on distant planets, it's to look for evidence of technology right here in our cosmic neighborhood. In our skies, in our solar system. These are not the actions of a scientific community that has dismissed the possibility of artificial objects visiting us. These are the actions of people who are preparing for the next one. And there will be a next one. The statistics guarantee it. Based on the rate at which we've detected interstellar objects in recent years, astronomers estimate that at any given time, there might be thousands of them passing through the solar system, most too small or too far away to spot. The Vera Rubin Observatory will change that. Within a decade, we might be tracking dozens of interstellar visitors per year. Most of them will be rocks, fragments of ancient collisions, shattered worlds, debris from the formation of planetary systems billions of years old, natural objects with nothing to teach us except that the universe is messy and violent and full of things breaking apart. But maybe, once in a while, we'll find something else. Something that moves like 3I/Atlas. Something that makes us ask the question again. There's a philosophical shift happening, subtle but profound. For most of human history, we assumed we were unique. Then Copernicus told us we weren't at the centre of the universe. Then Darwin told us we weren't specially created. Then Hubble told us our galaxy was one of billions. Each revelation pushed us further from the centre, made us smaller, more ordinary. But we still held on to one last distinction. We were the only ones asking the questions, the only intelligence, the only consciousness, the only beings capable of looking up at the stars and wondering, 3I/Atlas, whether it's a comet or something more, is forcing us to confront the possibility that even that last distinction might be wrong, that we might be ordinary in yet another way, that intelligence might be common, that civilizations might rise and fall across the galaxy like waves on an ocean, and that we're just one more species taking our first tentative steps into a cosmos already full of others who've been here long before us. How do you think that changes us? Knowing really knowing, not just suspecting that we're not alone. Some people find that thought terrifying. The idea that we're being watched, studied, judged by entities whose capabilities and intentions we can't fathom. The loss of our specialness, our centrality, our cosmic importance. Others find it oddly comforting. The idea that we're part of something larger, that the universe is full of minds and stories and civilizations, that the silence and darkness aren't quite as empty as they seem. I don't think there's a right answer to how we should feel about it, but I do think we're going to have to figure it out, because the universe isn't going to stop sending us visitors just because we're not ready for them. In the meantime, 3I/Atlas continues its journey. Right now, tonight, as you're watching this, it's moving outward from Earth, heading toward Jupiter, growing fainter in our telescopes, but not in our attention. Every observatory that can see it is watching. Every radio telescope that can spare the time is listening. Data is accumulating, models are being refined, and in a few months we'll have our answer. Or at least, we'll have more questions, because that's how science works. Every answer opens up new territories of uncertainty. Every discovery reveals how much we still don't know. And that's okay. That's the point. The joy isn't in having all the answers, it's in the journey toward them. In the moments of wonder and confusion and revelation that come from encountering something genuinely new. 3I/Atlas has given us that. Whether it's natural or artificial, whether it's a comet or a probe, it has reminded us that the universe is stranger and more surprising than we imagined, that there are things out there moving through the dark, following paths we don't understand for reasons we can only guess at. And it has forced us to ask ourselves a question we've been avoiding for a long time. If someone did send a probe to our solar system, if they wanted to learn about us without revealing themselves, what would they find? What would their observations tell them about who we are? What we value? Whether we're worth contacting, I'd like to think they'd see our curiosity, our determination to understand the universe despite our limitations, our willingness to ask hard questions and follow the evidence even when it makes us uncomfortable, our capacity for wonder. But they'd also see our conflicts, our divisions, our capacity for destruction. They'd see a species that has barely learned to live peacefully on its own planet, let alone venture beyond it with any kind of unity or purpose. Maybe they're waiting. Maybe that's what probes like 3I/Atlas are, for not to make contact, but to observe, to gather data, to wait until we've matured enough to join whatever community exists out there among the stars. Or maybe there is no community. Maybe they're as alone as we are, sending their scouts into the dark hoping for an answer that never comes. We don't know, but in 90 days, we might know a little more. And in the years after that, as we watch the sky more carefully, as we build better tools and ask better questions, we'll learn more still. The universe is patient. It's been here for 13.8 billion years. It can wait for us to catch up, and we will. Because that's what we do. We look up, we wonder, we build machines to extend our senses into the cosmos. And slowly, carefully, one discovery at a time, we find our place in the vastness. 3I/Atlas is part of that story now. A golden flash in the night, a visitor from the deep dark, a mystery we're still unraveling. And whatever the truth turns out to be, the fact that we're here asking the question, the fact that we care enough to watch and wonder and work toward an answer that might be the most remarkable thing of all. Thank you for staying with me through this journey. If you want to follow what happens when 3I/Atlas reaches Jupiter, if you want to be here when we find out what this object really is, make sure you're subscribed, because this story isn't over. It's just beginning. Keep looking up. The universe is full of surprises, and we've only just started to see them.